So there is a change of plans because I didn't talk everything that I wanted to talk in the first lecture. So today, first I want to finish what I wanted to discuss on Monday. And then I hope to have time to explain everything that I did about supergravity. Well, it's not going to be very detailed, but the basic ideas I think I can explain. And then in the last lecture, well, if I don't extend this one over here, then I will talk about compactifications. So here I already wrote some notations that I'm going to use. So sometimes I'm going to use a big letter A when I want to describe all indices of the superspace. Indices that transform under Lorentz transformations. So they are just rotations, usual rotations of vector and spinor indices. So the big letter A means that I run over all the indices here. And when I start talking about supergravity, I have to use a curved space indices. So the indices of the local coordinates of my curved superspace. So I'm going to use a big letter M to define all the curved space indices. So the small m is going to be the bosonic directions, and mu dot are the ones corresponding to the Grassmann odd directions. But it's important to differentiate between these two, because alpha and alpha prime, they are Lorentz indices, they are really spinor indices. Mu and mu dot, although they correspond to Grassmann odd directions, they are not spinors. They are curved space indices, so they do not transform under Lorentz transformations. They're going to transform the same way as n, so they transform under general coordinate transformations, but now extended to the whole superspace. Okay, I'm going to talk more about that later. So here are these differential operators are defined last lecture. So what I'm calling covariant derivatives, the derivatives that commute with the symmetry generators. Generically, I'm going to call nabla. So nabla A is just derivative of A. Nabla alpha is this combination. Nabla alpha dot is this one, and Q bar are the supersymmetry generators. This is also it's a shorter way to write this combination over here that appeared in my superfields in the last lecture, in my superfield last lecture. So sigma is just identity matrix and the polymatrices, and this combination here is this. Also, we're going to need to discuss the mass dimensions of the superfields, of the actions that we're going to write. So mass dimension of bosonic derivative is 1. It's just because it's a derivative of x. X has mass dimension -1. The differential of x also has dimension -1. So for that, here, there is a reason to say that the mass dimension of this operator should be half. So why is this consistent? Because I want the derivative of alpha to, when acting theta, to be 1. So derivative of theta should have the inverse mass dimension of theta. So the only way, if this has dimension 1, so the only way to make this consistent is if this is dimension half, mass dimension -half, and this one dimension half. So the biggest difference is when I talk about the integration measure. So integration measure in 4 dimensions has mass dimension -4, because each dx has mass dimension -1. But for the superspace, this is different, because we saw that if I integrate over theta, this is like derivative of theta. So when I integrate over thetas, this is not going to have mass dimension -half if I expect a correspondence between this differential and this differential. Because of this, the integration measure in the superspace has the same mass dimension as the derivative. Okay, this is a very important difference. That's why there is an exclamation mark here and here. Okay? So last lecture, I introduced the concept of superfield. Well, I started with a generic scalar superfield that I call phi. It's a function of the whole superspace. So now I'm going to write like this. So it's the big index A. So this means that it's x, theta, and theta dot. And I did a Taylor expansion in the Grassmann of the variables. For the first one, I called phi, small phi, and then this one. I don't remember the letters, but. Then there is one with theta and theta bar, the vector. Then theta squared f, theta bar squared f bar, then theta squared theta alpha. Well, I don't remember the name. I'm just going to call it chi. And then finally, call this one big F. I'm going to call it G value. So this superfield here has too many components. For example, if I have a scalar in 4 dimensions and I want to supersymmetrize it, I want these Q's to operate on this is the differential representation in terms of superfields. But if they have some other representation in terms of a composite operator corresponding of which is the conserved charge of the conserved current associated with the supersymmetry transformations, I want Q and Q alpha to just give me a new spinor. But here I have too many fields. I have, apart from the scalar, I have this psi's, I have this vector, I have these f's, and these chi's, and this g. It's too many things. So there should be a way to impose some condition on this phi such that I have fewer fields in my superfield expansion. So it's important to have one theory that's supersymmetric to talk about the constraints. So for each supersymmetric theory, there is a corresponding superfield, and this corresponding superfield have to satisfy a set of constraints. It can be just a simple constraint or something a little bit more complicated. If I want a supersymmetric theory containing a scalar and 2 chiral spinors, if I just want to have these components, the way to obtain a theory with these fields over here is to impose something that I call, to introduce something that I call a chiral superfield. Chiral superfield is an example of this. That's complex. And satisfies this restriction. This is not an equation of motion. This does not impose any differential condition in the components. Although it appears because this operator has derivative in theta bar and also has a derivative in x. So I remember that Max, in his first lecture, he emphasized that if I have an action and I have some constraint and I want to substitute back into the action the constraint that I'm imposing, it's important that this constraint should not be a differential constraint, should just be an algebraic constraint. So if I see exactly what this is giving me, I'm going to see that this is only giving me algebraic constraints. So I don't have to solve any differential equation to solve this. This is just an algebraic relation between the components here. Okay? So why it should be complex? So why I emphasize it should be complex? Well, suppose it's real. Suppose that phi. So let me suppose that phi, when I take the addition conjugate, is equal to phi. So what happens if this is true? So I take this constraint. Is equal to 0. So I take the emission conjugate on both sides. Well, the emission conjugate of 0 is 0, but the emission conjugate of this should be nabla alpha and phi. Because I'm saying that the emission conjugate of phi is equal to phi again. So if phi is real, this is 0 too. Why that's a problem? Because now I have these two conditions on phi. So I have that alpha, nabla alpha phi is equal to 0, and right now. So if I act with nabla alpha bar on phi, this is still 0, and now I start with the other one, the one that I wrote here. This is 0, so if I act with nabla alpha, this is still 0, right? Now I sum both equations. I get 0 again. But what is here is the anti-commutator of the nablas. But the anti-commutator of the nablas, as I discussed in the last lecture, here. So the anti-commutator of nablas satisfies this relation. So if I replace what is this in terms of the anti-commutator, I'm going to get that 2I sigma r, sigma a, alpha, alpha prime, del a, and phi is equal to 0. So this means that phi is just a constant. So that's the reason why phi should be complex, because if it's real, this chiral constraint that I'm defining by this equation is too strong, and in the end, my whole superfield will just be a constant. Okay? So that's the reason why phi has to be complex. Any question? Okay, now I want to see the consequences of this constraint. So I write what is now the bar. The bar is del bar of dot minus this combination here I'm writing implicitly the contraction between the alpha index that's here in the theta and one of the alpha indices that's here in the sigma. So I write it just in the alpha bit. Then I write my superfield. So it's phi plus theta alpha psi alpha theta bar alpha dot psi bar alpha dot, then theta A theta dot, this vector A. Maybe I should call it B because I'm using A for the index, but I hope the context makes it clear that this is the field and that is an index, that I didn't use it yet. Then theta square alpha not. Because so this should be 0. So I start going component by component. So if I derive with respect to alpha bar, theta bar, sorry. So this is 0, this is 0, but this is not 0. So the first non-zero thing that I get is psi bar. Then if I come here, so I have to derive with respect to this theta bar, but I have to pass, my derivative has to go over this theta. So I get a minus sign. Minus sorry, over here. So minus theta alpha A with an index alpha dot, my vector with index A. So then I go over here, I have to derive this guy over here. So theta square, each theta is a Grassmann variable, but theta square, which is the combination of two thetas, they behave like a boson because I'm going to go over one theta, then the other, so I get two minus signs. In the end, it's just a plus sign. Plus this. Here, so if I go by my definition, I'm going to get a 2. So this is 2 times theta bar alpha dot theta alpha chi alpha. And then this one, wait, did I forget something? No. This one is 0. This one is going to give me 2 again. 2 times alpha bar dot f bar. And then the last one is 2 times theta square theta bar alpha dot g. So now this is just the result of applying this derivative over everything. So now I have to do this step. So I apply here because derivative of x applies in every component because every component is a function of x, is a field of x. So minus theta sigma a minus I alpha dot derivative of phi, and in this one is minus I theta a alpha dot. Now there is another theta here. Derivative of a, then minus I theta alpha dot theta. I'm going to change this index to beta. And I go over here. This is going to be minus I theta A alpha dot. I'm going to change this index here to B. I don't know if I wrote enough terms to see that this is not a differential constraint. So, what happens if I try to apply this over here in this term?
Theta for the navigator?
Sorry, say again?
Theta for the navigator is theta 1.
This theta over here is just theta because the nabla bar. Oh, sorry. Thanks. There was a mistake here. Thanks. Yeah, here I wrote correctly, so there is no bar here. So this term is going to be 0 because there is one theta here and 2 thetas already here. But every time that I have 3 thetas, this is identically 0. So nothing happens applying this combination on this guy over here. So this guy over here, so it's not going to be 0, it's going to be something with 2 theta bars, 2 thetas, and a derivative of chi. We don't want to keep going because it's too much. This one is also going to be 0. This one, no, it's going to be derivative of f. And this last one is going to be 0. So now everything.
What happens with the epsilon in the R squared when you write?
Epsilon is a constant.
Yes.
So the epsilon is just going to raise. So I explained shortly last lecture that epsilon I'm going to use to raise and lower indices. So I'm not going to be careful with numeric factors and signs. Well, signs sometimes are going to be important, so I'm going to I'm trying to be careful. But there is a convention to say what should be the position of the indices for this to be theta with an index down. Because other possibility, which is different from this one, is if I define like this. If I define like this, my theta with index down is going to have a minus sign because if I transpose the epsilon, I get a minus sign because epsilon is antisymmetric. So I apologize for if there is some sign error somewhere, but okay, I want to be careful because I think the idea of how it works is more important than all the correct signs. Unless the sign is very important. For example, I don't know, I get a mass square that's negative, that's going to be a problem. So what does it say here? So each component, theta is a variable in the superspace. So each term here with the same number of thetas should be 0. So the only term with no thetas is this one. So I get my first constraint. Which is an algebraic constraint. So there is no differential equation for this to be 0. So the first consequence from this constraint for that a superfield that's scalar and complex and also chiral is that this component should be zero. So now I look for terms with only one theta. There is one here and another one here. What does it say?
We have AI minus partial phi equals 0.
So it's saying that my vector field that appear in the general expansion of the phi is not independent. It's going to be derivative of phi. So there is a minus I here, a minus here, so it should be minus I derivative of phi, which is also algebraic. I just replace A with the derivative of phi. I'm not solving any differential equation. The term with theta square should be somewhere. There's one here. The same is going to happen with chi. Chi is not going to be independent. Chi is going to be the contraction of the sigma matrix del acting on psi. So how do I have to do something here, which is this is anti-symmetric in alpha and beta. It should be proportional again to epsilon. There's a factor here that I'm also not going to be careful about. So there is a number here. I think it's half. It's not important. So there is a half here. So I use this epsilon to in this term to raise an index of sigma. And this index is going to be contracted with this psi over here, because this alpha is contracted with this alpha here in psi. So for this term together with this term to be 0, this is going chi alpha dot is not independent, is going to be some number here. I'm not going to calculate an I sigma A alpha dot, oops, then A psi alpha. And I can keep going. So included the other terms here. This big F, this G here, if I keep going, I'm going to find that G should be box of 5. If some number 2. So F, this F over here has to be 0, because if I look for here, if there is a term, another term with only one theta bar, there's not going to be none. So there is nothing that can couple, give me an equation for this F. This F is going to be 0. Also, this F over here doesn't appear anywhere, because there are 2 thetas here, there is 1 theta here, so there is theta cubed is 0, so this term acting here gives nothing, and there is only 2 thetas here. The derivative of theta bar acting here is also 0, so this F is free. So I get a list of constraints, all of them can be solved algebraically, and it's reducing the number of components. So I'm going to have phi, this psi over here, this psi should be 0. And that's it. The whole superfield is going to depend only on phi and psi and their derivatives. Is it clear why this is happening? So the reason that I didn't want to relate this psi bar with this psi is because if they are complex conjugates to each other, if this is 0, this is also going to be 0. So they are independent. When the field, the superfield that I started is complex, these two things are unrelated. Okay? Right, so this is a chiral superfield. It's going to have an expansion in thetas, and now I know that all the higher components. May I erase this part over here? So the chiral superfield now is a very simple expansion. I have my phi x, I have the theta alpha psi alpha. Another independent one is the f, because I get f bar equal to 0, but f never appeared in this expression that gives me, that's a consequence of this constraint. So f is still here in the chiral superfield. So there is a term that's theta squared f. So f is here too, but f is going to be what we call an auxiliary field. Doesn't have any dynamics associated with it. And all the higher components depend on derivative of phi, derivative of psi. It's not going to depend on derivative of f, but anyway, so I don't have to keep going. I know that all the higher components are going to depend on this. Okay? So together with a chiral field, I also have the anti-chiral field, which is another complex field that satisfies the Hermitian conjugate of this one. So an anti-chiral field that I'm going to call phi dagger satisfies this equation. If I write this equation in terms of components and solve them, I'm going to get something very similar to this, but if the rows replace it. So where I have theta, I'm going to have theta bar, and in terms, I have a psi, and now I have psi conjugate, and so on. So an anti-chiral superfield the superfield I'm calling phi dagger is going to have a complex scalar, and I'm going to call phi dagger. Depends on theta bar, alpha dot. Another field that I'm going to call psi dagger. And term which is theta bar squared f bar. To be consistent, maybe I should start calling this one up. It's not f bar was 0. I'm going to call it, to be consistent, f dagger. And higher components that are going to depend on derivative of phi, derivative of psi, and no derivative of f. F still remains just an algebraic field inside of the superfield. Okay? So that's how I reduce the number of components inside of a superfield. I look for a suitable constraint that's not going to give me any differential equation for the components, but just algebraic conditions. Now, so where is somebody should be asking? So where are the supersymmetry transformations? Because I want to have a theory that's supersymmetric, but up to now I'm just writing stuff in Superspace that seems very abstract, or it is very abstract, and writing these components. So now I can start looking for what are exactly the supersymmetry transformations. I'm going to call my supersymmetry operator SUSY. It's going to have a parameter, my supersymmetric parameter. I'm going to call epsilon, contracted with Q, and an epsilon bar, alpha dot, Q bar, alpha dot. And the supersymmetry transformation of my superfield, I'm going to write this in two ways. So the supersymmetry transformation acting on the superfield is represented by this differential operator. But the supersymmetry should have another representation for each component, which is not this one. It's something that I have to write in terms of the conjugate momenta associated with my field phi and so on. That comes from an action. So what I'm going to write this is here after the equal sign is this operator acting on each component. This one, and this one. So note that this operator is not Grassmann odd, because my supersymmetric parameter is also spinor, is also Grassmann odd. So the whole operator here is Grassmann even. So I don't have any sign plus or minus when I move this operator over the tails. So the operator acting on the superfield is the supersymmetric transformation of phi plus theta alpha, the supersymmetric transformation of the supersymmetric transformation of psi, and theta square, the supersymmetric transformation of f, plus the higher order in the theta expansion terms that are over here. So now is the time to use this as a differential operator. So I write epsilon q alpha, epsilon bar alpha dot q bar, acting on my superfield, which is writing only the first three components. Then I'm going to compare these two definitions. So delta SUSY phi is going to correspond to the term from this expression over here that contains no thetas. So I look for it. So where is which term after I replace q and q bar as differential operators acting here have no theta? Look that here, there are only terms with 3 thetas or more. There is no, the only terms, one that's important is exactly this one over here. So this one I should write. So yes, now the only, this is order theta q or higher. This one is important like this one. So I look for the only way to get no theta after applying these two differential operators in this expansion is when I derive with respect to this theta. Because these two terms over here are going to raise the power of thetas, right? This one lowers theta, the power of theta by 1, and this one lowers the power of theta bar by 1. But there is no, the only place there is a theta bar is here. So looking for only what I get from Q bar, I see that I'm going to derive with respect to this theta, and I get epsilon alpha psi alpha. This is a possible term. Another one that's important is the one that leaves me with only one theta. If I want one theta, the only term from here that is going to give me one theta, there is more than one. There is a possible, no, there is only one. So which one is it?
Theta squared f.
Sorry?
Theta squared f.
No, only one theta. I want to apply this over here, and I want something that's going to have only one theta that I'm going to call the index I'm going to call beta, to not confuse with the alphas that are going to appear here maybe. So what should I do?
When I apply it with this kind of field, the one applied to this kind of field.
It's so if I look over here, this is the way. So I'm going to have a minus I sigma A beta sorry, yes.
But why doesn't the same QA apply it over the theta squared times f term?
This one?
Yes.
Yes. That's also going to appear. Yes, you're right. You're right. I can derive this one, and it is going to give me. Oh, there is an epsilon missing somewhere. So the epsilon missing is. Is epsilon. Oh, wait. I made a mistake somewhere. Again, we'll write first this one is here. This is minus 2 epsilon alpha, theta alpha, f. So this one is clear. But I made a mistake somewhere. I want something that has one theta, because I want to look for the supersymmetry transformation of psi. No, it was right. Yes, no problem. It was right. So it is minus I theta sigma A with an index alpha. Alpha dot I epsilon bar alpha dot derivative A of phi. So this one comes from Q bar, this over here, contracted with an epsilon bar, acting on this component over here. Right? There is also going to be a supersymmetry transformation for f, but I don't. It's important, but I don't want to write it here because it's not fundamental. The first two are the most important ones. So this one defines the supersymmetric transformation of phi, and this combination over here defines the supersymmetric transformation of psi. So the supersymmetric transformation of F is the result, looking for applying this operator in this combination, the term that gives me two thetas. Okay? So supersymmetric transformation of phi is epsilon alpha, psi alpha, and the supersymmetric transformation of psi alpha, or alpha, is epsilon bar alpha dot theta a alpha dot derivative of plus this term of it minus 2 epsilon alpha f. So the supersymmetric transformation of psi also depends on f, not only on phi. So this term here is important to have something that we call off-shell supersymmetry, that I don't have to use equations of motion such that the supersymmetric transformation is closed. Closed under the algebra of supersymmetric transformations, because if I apply with two supersymmetric transformations, I should get a translation. Okay, so this is the recipe. If I have a superfield that has the appropriate constraints, I solve the constraints, I find the minimal set of fields that describe the whole superfield. In this case, is phi, psi, f. For the anti-chiral, is phi dagger, psi dagger, and f dagger. And I calculate what are the supersymmetric transformations with this recipe. First, I represent supersymmetric transformation in each component. And then in the other side, I represent the supersymmetric transformation as the differential operator acting on the superfield.
The first step of the supersymmetric transformation of psi alpha shouldn't have the theta.
Maybe I forgot something, but it's not going to change here. Maybe there is another term. So there is this one that comes from Q bar, and another one that comes from Q bar that comes from here. Because Q bar, there is a derivative of theta bar, so it's going to derive this one that gives me something similar to this. I think I'm going to have a 2 here at the end.
Theta should not be there.
Sorry?
Theta should not be there.
Theta is
Theta is not there.
theta.
In the first step?
Yes, I didn't understand what you said.
You factorize it.
I have to?
Factorize it.
Ah, yes. I have to factorize. Ah. Right.
Then you don't have it.
Sorry. You're right. Right. When I compare both expressions, is what's important is what multiplying theta. Yes. Yeah, I should have seen it, because if I write a theta here, it's going to contract with this index, and there is no alpha index on the right hand side. All right, and now I know how to reduce the number of independent components. I know how to calculate the supersymmetric transformations, but I want to have dynamics. I want to write an action of it.
Professor, under what consideration you write a constraint like this constraint? You can.
How do I know this is the correct constraint?
Yes.
Because I write in some paper. Well, it's somebody in the 70s derived for us. So there is no algorithm. So in the case of, this is the simplest superspace and supersymmetry in 4 dimensions. We call n=1 supersymmetry. n=1 because there is only one set of supersymmetry transformations. There is only one Q and one Q bar. I could have a bigger set with 2 Qs or 3 Qs or 4 Qs. So this is going to raise this number to 2, 3, 4. Okay? So this one is n=1 SUC in D=4. Okay, in 2 dimensions it's even simpler, but if I want to describe physics in space-time, I have to start with D=4. So this is the simplest supersymmetry I can have in 4 dimensions. So if I want fields with a spin lower than 2, we already know all the possible classifications of superfields describing the appropriate multiplets for 4 dimensions. So we know what the constraints they satisfy, what are the actions, and so on. I think even for higher spins, even if I want higher spin theory is a very interesting topic in theoretical physics. So there is also a classification of all higher spins from 2 to infinity in terms of superfields for describing n=1 supersymmetry in 4 dimensions. So this is known, it was classified. It is not, there is no algorithm. These are research papers that look for these constraints. So it's not obvious, it's not, there is no intuition to find something like this. Of course, after 20 years, we know more or less intuitively why it makes sense. So why it makes sense is because it does not impose any differential constraint. They can all be solved algebraically. Okay? That's basically the main reason.
But the constraint is some degrees of freedom of the superfield.
Sorry, say it again.
The constraint kill degrees of freedom of the superfield.
Not yet, because I don't have exactly. It doesn't. It does not reduce the number of degrees of freedom. It's just saying that the higher components they are related to the first components. In some sense, yes, it's reducing the degrees of freedom because I'm eliminating everything that appears here. But there is no dynamics associated. For example, why I know that the photon has only 2 degrees of freedom. It does not come from describing the photon in terms of a vector superfield, a vector field. I have to know what is the action, what is the gauge invariance, and so on. This is just algebra. Okay? That doesn't have any dynamics. So that's what I want to talk next. So how do I describe dynamics using superfields? So I want to write an action. I'm going to raise it here. So first, just a scalar field in 4 dimensions. So if I want, so why do we know that if I write this, why do we know that this action describes a theory that's Poincare invariant in 4 dimensions? So why we look at this and we automatically know that it's going to be invariant if I transform my coordinates by some constant vector epsilon a.
You do the variation and you get a boundary term of 0.
What?
You do the variation of the action and look to have a boundary term of 0.
Yes, but if I'm integrating over the whole space, there is no boundary.
Scovaio.
So there is no boundary. The whole I'm integrating over the whole space.
But you get zero.
Because
You get zero if you do the variation.
yes, exactly. So if I integrated the whole space and everything that I write here is local, is written only in terms of fields and their derivatives, it's guaranteed that it's going to be invariant under this delta x. So I want to apply the same philosophy for writing supersymmetric actions. I want to have a functional of my chiral superfields, because they're the first ones that I'm describing, that follows the same philosophy. I want to integrate over the whole superspace, not only the for x. So I want to integrate over my whole space, but also on my whole superspace. I want to write an integration measure for the thetas and the theta bars. Okay? So now I have to worry about the dimension of the measure, the integration measure, and the dimension of my superfield. So a scalar field in 4 dimensions. What is the mass dimension of phi? I can see from this. So the action should be dimensionless, but we know it's c equal 1 and h bar equal to 1. So the action is dimensionless. So if this has mass dimension -4, one derivative has mass dimension 1, another mass dimension 1, so phi should have mass dimension 1. So if I go here to my superfield, the whole superfield should have the same dimension as its first component. So if I wanted the first component to be a normal scalar field in 4 dimensions, the whole superfield should have mass dimension 1. Now I look here, so what is the mass dimension of this whole combination? It's -4 from dx. Then I go over here, this very important point over here, that each differential, it's not differential of theta, it's the integration measure over the superspace variables. So each one has mass dimension half. And there are 4 here, 2 from theta and 2 from theta bar. So I have a contribution from here to mass dimension 2. All right? Well, if I want my action to be dimensionless, the only thing that I can write here is something with mass dimension 2, right? I don't have any other option. So what can I write here that has mass dimension 2? A superfield.
Square, right? A square of the superfield, right? 2 times.
Yes. So suppose I start with phi squared. So what's going to happen if I try to integrate over theta and theta bar? So remember that one integral over theta alpha, this is equal to derivative of alpha, right? But after integrating over theta, I'm going to integrate it over the space-time, and I'm going to assume there is no boundary. So if there are boundaries, I have to be more careful, but suppose that there are no boundaries. So after integrating over theta, I'm also going to integrate over x. So nothing changes here on this side. If I add something here, that's going to be a total derivative. So I can complete this derivative with respect to theta with this term over here, and nothing changes. So this combination over here is equivalent to this. Same way, if I look in terms of theta bar, if for x one integral in theta bar is exactly the same in the case of there are no boundaries as, oops, there's a dot here, same as this. So this term is not going to work because I can replace this integration measure over theta bar as 2 nabla bars, right? So a nabla bar kills phi, so this is going to be 0. If I try to put phi dagger square, I have the same problem because its integration measure in the variable theta I can replace with this, and the nabla alpha kills phi dagger. So now we are running out of options. The correct one is 5 phi dagger. That's the simplest supersymmetric action in 4 dimensions. This is going to describe a scalar field together with an action for these value spinors over here. So how that's going to happen? So this thing over here, right? What this is doing is selecting the highest component, the component here that has the most thetas. So theta squared and theta bar squared. So I multiply this one by this one, and look what has theta squared, theta squared. Remember that here there is a theta sigma A, theta bar, del phi A. There's going to be something similar here, but now with phi dagger. When I multiply this guy by this guy, I have a term with 4 thetas, which is del A phi dagger. So when I compute this, I know there's going to be a term which is exactly the action for a complex scalar. It's going to be del A phi dagger. The term for the fermions come in a similar way, because remember that there is a term with theta bar, theta bar square theta, which is theta squared theta bar, which is the derivative of psi. That's going to pair with this one, that's going to give me the Dirac action. When I keep going, I find everything that I want. This is the way to compute supersymmetric actions. So the fact that I'm integrating over the whole superspace, it assures me that the result is going to be supersymmetric. Maybe I should go way faster because it's already 12:15. Okay, so next to superfield is one that's called a real superfield. It's a superfield that depends on the superspace coordinates that satisfy just a reality condition. Seems to be not enough. Because if I just impose a reality condition, if you remember the first expression of the generic superfield with no constraints, it's going to have all of those components, and the reality condition is only saying that when there are no thetas, the field is real. For example, the first component is going to be, I'm going to call it C is everything. Then there is a theta psi alpha, psi bar alpha dot, psi bar plus theta sigma alpha theta bar A plus blah 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 blah. So gravity conditions just saying that this is real. This psi is the complex conjugate of this psi. This guy over here is going to be real because if I do the dagger of this combination, I get exactly the same combination. Now you can check using the rules and the definitions. But this is going to say this reality condition on the whole superfield imposes that this vector here is real. Then I'm going to have theta squared, theta bar, a reduced psi, plus and so on. So the reality condition implies that this chi is the emission conjugate of this chi over here, and it's going to be the same for everything. So this appears to be too strong. So that's why people 40 years ago realized that a real superfield should have a gauge invariance. Because this reality condition is invariant if I add to my real superfield V a chiral field, I'm going to call phi again, plus phi dagger. Because if V is real, V prime is also real. Because if I take the emission conjugate of V, so I started with V that is real, its emission conjugate is the same. But for phi, if I take the emission conjugate, it's a chiral field, so I get phi dagger. And if I take the dagger of phi dagger, I get phi. So I get again a field, a superfield that's again real. So the real superfield is always defined up to this gauge transformation. So what appears in the theta bar component of phi and phi dagger? It was written somewhere here. If I have a chiral field, I write its expansion. Blah, blah, blah. There was something here. What was here? Right. So phi is complex. So phi plus phi dagger. What's going to appear here is derivative of phi plus phi dagger. But phi plus phi dagger is real, right? Okay. So what I get in this particular component is derivative of a real parameter. All right? So now I go to my original vector superfield that has a vector exactly here. So if I define this gauge transformation of a vector, I'm using V vector superfield, it's real. If I define this gauge transformation of a real superfield, what is the gauge transformation of A?
What do you call it gauge transformation?
Because
Gauge transformation usually is that you have something invariant.
Uh,
This is not invariant, this is the transformation. It's like a definition of a field that.
Did I use the word invariant?
No, but
No.
Gauge transformation usually refers to invariant under something. They are not leaving something invariant. They are just different.
Nothing is
Invariant
invariant.
a real thing.
Nothing is invariant.
That's what I'm saying. So do you call it gauge?
Yes, this gauge transformation.
Why do you call it gauge transformation?
Well, exactly the answer to my question here. So, if this is the component that has theta bar in my real superfield, and if I'm saying that a real superfield has this gauge transformation, because if I start with V, I add a chiral and an anti-chiral field, I again get a real superfield. So I'm saying that V and V prime should be equivalent, right? So everybody saw that what appears in this sum of phi dagger and phi is derivative of a real parameter. So what is A prime?
Okay, sure.
Maybe if some coefficient here that I don't care. What's important is that this is real. This is exactly the gauge transformation that I expect for a photo.
So you're not imposing the other one. It's only this one. Only gauging, but not imposing the reality condition of B equals B dagger. Or you are imposing the two conditions.
Sorry, let me say it again. If I start with V, that's real,
Yes.
and I add phi plus phi dagger, it's again real.
So it's too weak. The first one is too weak, and we are in another
No,
one.
it's not weak. I'm saying that this condition
Yes.
is invariant. Okay, now I'm using the word invariant. This condition doesn't change if I add something that's a chiral field plus an anti-chiral field.
No, yeah, but I mean, if you only apply the first one, it's too weak. The constraint is too weak. You have to impose the gauging additionally to reduce the degree of freedom.
I see what you're saying. Let me think how. It's not that it's too weak. I see that this condition is not unique.
Okay.
I can always add something to V that's still going to satisfy the same condition.
Okay.
It's not that it's too weak. There is a freedom. There is a freedom associated with it. So this freedom is, the consequence of this freedom is that the vector field that appears in this component of my original V has a gauge transformation that comes from adding these two terms over here.
Okay.
So in the end, this V is going to describe the photon and its supersymmetric partner, which is 14. So that raises the question, so what happens with these lower components here? Because again, a vector superfield in 4 dimensions should have mass dimension 1. So this thing over here should have mass dimension half, and this thing over here should have mass dimension 0. So the whole superfield has mass dimension 0. So there are no, we don't know, but there are known fields in 4 dimensions with a mass dimension that low. So this all of these guys here, they can be eliminated by exactly this gauge transformation. So there is, I cannot call it psi again, I'm going to call omega. There is an omega here, which is exactly the linear component in theta. I can use this omega to remove this guy, and the omega dagger that's going to appear here to remove this guy. And the C is exactly this thing over here.
This is related to the fact that you don't have Majorana fermions in dimension 4, or is not related to that you have to eliminate the fermions.
Majorana fermions. I can have. Yes, I don't have what I have. If I have chi, I have to. If I have chi bar, I have to have chi.
Yeah.
Yes. So yes. Alright, so this is the superfield that describes supermaximum in 4 dimensions. So the action is a little bit more complicated for V, but it's not hard to describe it. So something that I can do is to define, so this is V, it has the gauge field in its components. So one could ask, where is the field strength? Because there should be a field strength associated to my superfield V, something that's invariant under this gauge transformation. So I'm going to write it here again. So the gauge transformation of the Vallilo superfield is to add a phi and a phi dagger. So how can I compute, how can I use my covariant derivatives over there to define another superfield in terms of V that's invariant under this transformation? So I can start in a simple way because I know that phi and phi dagger are chiral. So nabla alpha of phi dagger is 0 and nabla bar alpha dot phi is 0, 2. So I can start with, for example, nabla alpha v. If I compute what is nabla alpha v prime, I replace what is v prime. First nabla alpha. So v prime is v plus phi plus phi dagger, right? So this is the right way because nabla alpha kills phi dagger. So I know I'm in the right direction. So this is going to be nabla alpha v, nabla alpha phi, and phi dagger. You tell me phi dagger because phi dagger is anti-chiral. But I still have this one. I should be able to kill this guy over here, adding nabla bars. Right? So let me try nabla alpha and then nabla bar alpha, again on v prime. Oops. So this guy is already going to be killed by this one. So I have nabla alpha dot nabla alpha v plus this is the right direction. This is not 0 because I know that phi bar kills phi, but nabla bar kills phi, but nabla bar is not acting on phi, it's acting on nabla phi. To kill it, I have to change the order. Then I use the algebra. So I know that so I move this term over here. Now I use this identity, so I move the nabla bar over here, but I have to bring this term over here. It seems that does not help, but it does.
But you can add the action of the torsion over P, right? To the action, and that's what to cancel this term.
No, I
No?
need to do something else. Because the nabla alphas, they commute with del A. Because the nablas alpha, they don't depend on X. So the nabla alpha, I can move del A.
Ah, okay.
So if I add with another nabla bar, it's going to kill this piece over here. So that's the answer. Because now I can move this guy over this derivative. Oops, this is big file. Sorry. I can move this derivative over here, and it's going to kill this term.
You are taking derivative again, right?
Sorry?
You are taking the derivative again, right? On the left hand
That's it,
side?
yes.
Okay.
Sorry.
But this is not Hermitian.
This is not real.
This is not real, right?
Yes, but no problem.
Ah, no.
Because I can do, there is going to be another field strength.
Ah, okay.
The one that starts with nabla bar alpha and then two nablas without bar.
Yeah, you make it real. Okay.
Okay. So this is anti-symmetric in the index, so this is proportional to epsilon. So I can write this as nabla bar squared. So this is the end, the final answer. I have two field strengths. Let me. I think there is a numeric factor here for some reason. Maybe it's -1/4. I don't remember. So these are the field strengths. The first component of W is chi, and F is going to appear in the next one. So the F's appears in the second component of W and in the second component of W bar. And the action we write in terms of the W's. So if I want the action for the supersymmetric theory that contains the photon, now I have the mass dimension problem again. If I include two problems in fact. If I add here to the integration measure d theta squared and d theta bar squared, there is nothing that I can write that's gauge invariant, because my W's are now gauge invariant, that's going to survive this integration. Because this one is nabla bar squared and this one is nabla squared. So this is going to kill the, for example, W squared and W bar squared. But it also has the problem of the mass dimension, because the dimension of the physical spinor in 4 dimensions is 3/2. So W has that mass dimension 3/2. If I include this, I'm going to see that there's going to be too many, the mass dimension is going to be too high. So there is a way to solve this. Actually writing this. Let me write two things. This is not real because it depends only on integration over theta and the W's that are not real, but I add the complex conjugate. And this is the supersymmetric action for a gauge, an abelian gauge field together with its supersymmetric partner, which are these two components over here. Why it's supersymmetric? because this is going to be chiral, and this is going to be anti-chiral. Yes, this is anti-chiral and this is chiral. So if you remember the expansion of a chiral field, if I try to select the component that has 2 theta bars or 2 thetas, it's going to be a total derivative. And since I'm integrating over the x, so this is going to be supersymmetric. So there is it's not, when something is chiral, I know that if I integrate only over the thetas, it's going to be supersymmetric. If it's anti-chiral, if I integrate over only the theta bars, it's also going to be supersymmetric. That's also how I add the mass to the chiral superfield action. So usually mass terms, they appear with mass squared, which obviously has mass dimension 2. So I'm going to have a problem if I try to add a term with mass squared and a combination of phi's. It's going to have too much dimension. I cannot integrate over any theta because mass squared with phi squared already has mass dimension 4. So the mass terms will appear not with m squared but with m. And that's why the auxiliary field in the scalar superfield that's already disappeared, the F, is important. I can even say that this parameter here is complex. This is not going to mean that the mass is complex. The mass that I get in the end is going to be the term with mass squared is going to be this times this. So the phase that appear here in these m's, they disappear. So these are the mass terms for the chiral field. So, yeah, I think the compactification part is going to be 5 minutes in the last lecture. Because it's not going to be enough to talk about supergravity if we go in this way. So, any final?
There is no time for questions.
Okay.
Let's thank to